This is a clip from the Netflix series Three-Body Problem. Due to fundamental scientific experiments being interfered with by the Sophons sent by Trisolaran civilization, humanity is unable to obtain rational experimental results. One scientist loses her belief in the utility of science and jumps from a massive scientific apparatus and chooses to commit suicide. Although this scene is presented through post-editing, the massive apparatus in the picture is actually real. Also, while diving isn't allowed here, you can actually go kayaking inside. This apparatus is called the Super Kamiokonde experiment. It is located in the Kamioka mine in Japan, about 1 kilometer underground. It is about 300 kilometers from Tokyo. The Super Kamiokonde experiment is essentially a massive water tank. When running, its interior must be filled with 50,000 tons of ultra-pure water, which is highly purified and contains almost no ions, particles, bacteria, or dissolved gases. But be careful, ultra-pure water is not drinkable. The reason why Super Kamiokonde needs so much ultra-pure water is to detect a mysterious microscopic particle, the neutrino. So what is a neutrino? Why do we want to detect it? First, let's understand a concept called the Standard Model, or the Standard Model of Elementary Particles. It is a theoretical framework that has been developed since the last century. It tells us that this world is made of these indivisible elementary particles. For example, the familiar electron is an elementary particle, and the protons and neutrons in the atomic nucleus are composed of up and down quarks. Atoms composed of nuclei and electrons further constitute the various objects in our daily lives, including yourself. The Standard Model is a very successful theory. It brings together the results of countless physics researchers, successfully describing these elementary particles that make up the world and how they interact. And today's protagonist is the neutrino. There are three kinds of neutrinos called electron neutrino, muon neutrino, and tau neutrino. Even among these various elementary particles, the neutrino is quite special. It has some magical property. First, it is very small. Its mass is nearly zero, millions of times smaller than an electron, if not more. However, they are so abundant, they are everywhere. The sun, the earth, nuclear power plants, and even the banana in your hand are emitting neutrinos at all times. In fact, every second, trillions of neutrinos pass right through your body. But don't worry about any radiation, because it also has another property. It is very hard to detect. Its reaction probability is extremely low. It takes a piece of lead a few solar systems thick to block a single neutrino, even if every second you are bombarded by countless neutrinos. In your entire life, probably only one neutrino will hit you. Neutrinos are so abundant, so small, yet so hard to detect, so it is also called the ghost particle. So since it is so difficult to detect, what does it have to do with us? In fact, neutrinos may contain the answers to some fundamental scientific questions. The Nobel Prize in Physics in 2015 was awarded for the discovery of neutrino oscillation. This phenomenon proves that the mass of neutrinos is not zero, while the Standard Model predicts that neutrinos have no mass. This is so far the only place where the Standard Model has failed. Neutrino oscillation is a wonderful phenomenon. It means that these three kinds of neutrinos can transform into each other. It's like a basketball turning into a football while flying. Then, while continuing to fly, it turns into a tennis ball. Of course, this change does not happen suddenly. This oscillation curve represents the change in transition probability as the neutrino travels. But why does it mean that neutrinos are not massless? Here we can use tuning forks as an analogy. I secretly borrowed these two tuning forks from a high school physics lab. Let's tap it. Then we take out a piece of gum, clay, and stick it on one of the tuning forks. Let's tap it again. When we put the two tuning forks together again, you will hear the reason for the oscillation phenomenon is that the mass of this small piece of clay makes one tuning fork heavier than the other. In other words, there is a non-zero mass difference. Since this oscillation shows that different neutrinos have a mass difference, then the mass of neutrinos is not zero either. After saying so much, how exactly do we detect neutrinos since they are so small? It is precisely why we have to build the detectors so big. In fact, Takaaki Kaihita, one of the two physicists who won the Nobel Prize for discovering neutrino oscillation, was the main leader of the Super Kamiokande experiment at that time. We know that 60% of the human body is water. Then 50,000 tons of water is equivalent to 500,000 of you. Then a reaction that happens once every 100 years on your body can happen dozens of times a day in 50,000 tons of water. Of course, the detection efficiency must also be considered, but even so, since its operation in 1996, the Super Kamiokande experiment has detected tens of thousands of neutrinos. When a neutrino, by a tiny chance, interacts with an atom in the water, it will emit some charged particles. If these particles move fast enough and exceed the speed of light in water, they will emit a light ring called Cherenkov radiation. Super Kamiokande sees neutrinos indirectly by detecting this light. In fact, those dense things that we saw before inside the detector are a type of light detector called photomultiplier tubes. The people kayaking inside are not there for fun, but are researchers and technicians installing or maintaining these tubes. It is through these eyes that we can see images like these. Each light ring corresponds to a charged particle, and only a tiny fraction come from neutrino reactions. The rest are likely noise particles from the background. This needs to be further analyzed and filtered. Looking at the history of Super Kamiokande, its predecessor, the Kamiokande experiment, first detected supernova neutrinos in 1987, winning the 2002 Nobel Prize in Physics. Super Kamiokande, as its successor, is more than 10 times larger, and won the 2015 Nobel Prize by observing neutrino oscillation. In the future, Super Kamiokande will be further upgraded to Hyper Kamiokande. It will study the neutrino oscillation phenomenon more finely, including determining the neutrino mass ordering and its charge parity conservation property. What kind of unexpected discovery will happen then? No one can foresee. At the same time, the US is promoting a project called the Deep Underground Neutrino Experiment. It plans to send neutrino beams over ultra-long distances underground to explore more secrets of neutrinos. And in China, the Jiamen Underground Neutrino Observatory, another next-generation neutrino experiment, completed construction in the second half of 2025 and has begun operation. Located in Jiamen, Guangdong Province, it detects neutrinos from the Taishan and Yangjiang nuclear power plants. Through a spherical liquid scintillator detector over 30 meters in diameter, it accurately measures oscillation parameters. After only 2 months of data collection, Juno released its first set of physical results. The measurement precision for certain parameters surpassed the total of all measurements from the past few decades. These next-generation, large-scale experiments are not only competitive but also cooperate closely on many scientific questions. In the process of construction, they have also driven the development of related technologies. In the novel, The Three-Body Problem, The Trisolaran civilization uses sophons to interfere with human large-scale scientific devices, preventing breakthroughs in fundamental science to lock down human technology. In reality, although fundamental research rarely brings direct benefits in the short term, it is these seemingly useless explorations that repeatedly drive the leap of human civilization. This has been particularly evident in the past 100 years. Who can predict whether the tiny neutrino will lead to new applications or even trigger a technological revolution? If you like our video, please like and share, and feel free to tell us your interested areas in the comments. If you are also a researcher and want to share your work with others, please contact us. Follow us, and welcome to Spinach University.